Increasingly, in data analytics applications across a variety of domains, data analysts are faced with the challenge of finding insights from high-dimensional data of mixed types. We introduced Sirius as a proof of concept for a novel data agglomeration strategy for exploratory data analysis using mutual information to find feature sets of interest. Our specific system is for data sets that contain a mixture of continuous and discrete data types with upwards of 50 features. In existing visualization literature, there exist a number of systems for high-dimensional data exploration. However, in our discussions with analysts, many of these tools come up short for a few different reasons. First, visualizations like parallel coordinate plots, radar charts, and pair plots may be sufficient for 5 or 10 features, but do not scale to visualization of, say, 100 features. Second, many of the existing tools for high-dimensional data exploration that use other encodings, like matrices and network graphs, are designed only for continuous or discrete data, not a mixture of both. Some visualization systems do exist for comparison across discrete and continuous data types, but they do so by discretizing continuous data into fixed-width bins, thereby potentially obfuscating important qualities about the data. We leverage the network graph as an encoding as well, but present a novel approach for weighting edges based on mutual information, which selects the optimal mutual information approximation based on the data type to be visualized. Therefore, continuous feature pairings are evaluated using a probability density mutual information algorithm. Continuous discrete feature pairings are evaluated using a nearest neighbor mutual information approximation. And discrete feature pairings are evaluated using the standard probability mass mutual information algorithm. From here, we are able to construct a mutual information feature network wherein dependent features of either data type are presented as nodes connected by an edge. A user of this system would use this Python package to compute the mutual information feature network of their tabular data, and then launch a dashboard for exploration of that network. The network suggests feature pairings that are informative, and users can rapidly iterate through a number of suggested pairings in order to formulate hypotheses about the data. As a case study, consider, for example, a data analyst in the real estate business named Miriam, who has just received a new dataset from a third-party data broker. Miriam is hopeful that this data set will provide her with new insights into the homes in her area, but she's also skeptical. Is this data clean? Is it accurate? Are there dangerous assumptions lurking under the surface? Before Miriam dives into complex data transformations and machine learning approaches, she just wants to look at the data with her own eyes. She needs a tool that will not distort raw data and give her a combination high-level overview, but also visual representation of the individual data points. Unfortunately, this data is very wide, almost 100 different columns, and viewing bivariate plots for every pair of features, like in a scatter plot matrix, would be a lot of plots to look at, well over 1,000 unique visualizations. Additionally, the data is a mix of discrete data, like the name of the home's neighborhood, and continuous data, like the home sale price. She needs an exploratory visualization tool that supports mixed data types for her analysis. Luckily, Miriam has Sirius. She uses the Python module to compute mutual information across all feature types, then launches the visualization dashboard. An important step in early analytics pipelines is confirmation of hypotheses and verification that data is recorded correctly. For this sort of confirmatory analysis, Sirius offers useful insight. Here, we see a discrete continuous plot of house style versus second floor square footage. As expected, the second floor square footage of homes is higher in 2-story and 2.5-story homes, followed by 1.5-story and split-level homes. Miriam is assured that these two variables are labeled correctly and considers that if she needs a continuous variable for another prediction algorithm that is dependent upon the discrete variable style of home in her dataset, she can consider the second floor square footage continuous variable as a potential candidate. Now Miriam is looking for potential feature pairings from which to extract new features of greater utility in her workflow. For this task, zooming in on particular network components may prove useful for finding extraction possibilities. Here we see a strong linear relationship along the axis x equals y, which indicates that, for many homes, the garage was built at the same time as the house. Therefore, it may be of interest to an analyst to extract a new feature for the difference between garage year built and year built in order to identify homes in which the garage was built much later than the house. Curiously, Miriam also sees some points where x is less than y, which could be errors to be targeted by data cleaning or follow-up, or may indicate that these are homes where the house was demolished and rebuilt, but the garage remains from the old structure. Miriam resolves to call the data broker to ask, and perhaps look up some property records for the homes where x is less than y, before she moves forward with combining these two features into a new feature which measures elapsed time between when the house was built and when the garage was added. Now Miriam considers another analytic task, the identification of potential predictive features. Here, Miriam sees a suggested plot from Sirius showing garage cars compared to garage area. Aha, this could be useful. It just so happens that from another data broker, Miriam's company has segmented satellite data of additional homes that are missing from this data set. It might be possible, using this known relationship, to predict the number of bay doors on the garages of those satellite data homes without having the street-level data or documentation to indicate the number of cars that the garage can accommodate. Miriam is happy because she knows that customers on their websites sometimes like to filter homes by how many cars the garage can fit, and the satellite data homes that are missing this information currently are dumped when that filter is applied. Now Miriam has an idea of a way to backfill that data using a new feature relationship she has uncovered thanks to Sirius. In a dataset that has been properly anonymized by randomly assigning IDs to records, Miriam expects that the ID number should not appear in the Sirius network graph, because considering the ID number as a continuous measure should not, statistically speaking, offer any benefit for mutual information, and should not be dependent on any other variables. However, in this case study dataset, the ID feature is present in the Sirius network graph. Miriam knows that this indicates that the ID value actually contains some information about the nature of the individual records. As we see here, there are complete ranges of the ID number that correspond to the pool quality. This is a curious artifact which indicates that either IDs are not randomly assigned, or possibly that the pool quality data is synthetically generated. Miriam resolves to investigate further by contacting homeowners about their pool quality and also asking the data broker how that data was either collected or modeled. Optionally, Miriam can now choose to adjust the feature network by selecting higher or lower alpha significance values from the viewer below. The alpha significance chart shows the number of connected components, the number of connected edges, and the ratio of the size of the largest to second largest component in the network graph. By adjusting the alpha significance, Miriam is able to generate a mutual information network which is more or less dense to adjust her overview of the data. Additionally, Miriam may opt to change the network graph layout from a force-directed spring layout to Kamada-Kawai. The spring layout algorithm, known as Fruchtem and Reingold, positions nodes according to an iterative algorithm that assumes that nodes repel each other when close, but are attracted to connected nodes. Convergence is obtained by using a simulated annealing style technique with an arbitrary cooling function. In contrast, the Kamada-Kawai graph layout attempts to position nodes on the space so that the Euclidean distance between them is as close as possible to the graph theoretic distance. Both layout options are included, and subsequent user studies may offer a suggestion for which layout is preferred by data analysts. From these 4 tasks, we can see the utility of Sirius as a system for exploration of mixed data types in high-dimensional exploratory analysis workflows. The novel contributions of this system include the automated selection of mutual information algorithm implementation based on data type. Similarly, the determination of chart type based on bivariate data type pairing, and additionally, a network sparsification step that is context-aware and trims edges in the feature network by their statistical significance, rather than some arbitrary static threshold which might overemphasize identical feature pairings and hide more unusual feature dependencies.